So let's talk about a new topic in math, the idea of absolute value. Absolute value is kind of weird because you've never thought of numbers in this way. Since grade 7, you've been dealing with positive and negative numbers. And now all of a sudden with absolute value of numbers, we're going to be asking you to disregard the negative part. Well, that's a little bit hard to explain just by talking, so let's use some examples here. This is page 166 of your workbook. It might be best to approach the idea of absolute value by looking at a couple of examples before we start looking at a definition. So an absolute value function is denoted by two vertical bars with a value or an expression or even an equation inside. And the first example here is asking for the absolute value of 5, and positive 5 is implied. And the absolute value of 5 is simply going to be 5. Easy peasy. Well, let's look at another example. This can't be too hard. The absolute value of negative 100. Well, the absolute value of negative 100, I'm going to tell you first, and then we're going to discuss what it actually means, is 100. All right. Well, let's do something a little bit more complicated here. The absolute value of 3 squared minus 25. Well, we can do some simplification inside the absolute value signs. 3 squared, of course, is 9 minus 25, like that, will give us the absolute value of, negative 16? And the absolute value of negative 16 is going to be 16. So what have we done there in these three examples? We've had a positive number 5 stay at 5. We had a negative number of 100 go to, looks like positive 100. And then we had a negative 16 seem to turn around into a positive 16. So what is it that's happening when we ask to do the absolute value? Well, the absolute value of a number or a function has to do with distance. And what we're looking at now is the distance between the value of your function or the number and 0. So if 0 is right in the middle here, this is 5. What we're looking for is the actual physical distance between 5 and 0, which in this case is pretty obvious to be 5. For negative 100, which will be way over here on the number line. I'm going to scroll up a little bit. Again, what we're looking for is the physical distance between negative 100 and the 0 line. And you can see very easily and very quickly that the distance between negative 100 and 0 is simply 100. And we got that simply by removing the negative sign. But I want you to start thinking about absolute value as being a distance. Since grade 7, we've been training you to think about numbers on the number line and including both positive and negative numbers. Now we're going to start asking you to take a look and think about numbers and expressions and values, not as positive and negative, but simply as distances. Distances from 0, because that's what absolute value is doing to a number or an expression or an equation. It's asking you how far from the x equals 0 part of a graph or x equals 0 part of the number line do the different possibilities for the function fall into. It's easy to calculate absolute values when you're looking at numbers. It's a little bit more complicated when we're dealing with functions now. So we're going to be putting functions inside absolute value symbols and trying to figure stuff out. So let's do a simple function, that one that you've known and loved forever. F of x equals x, all right? And I want you to think about what f of x equals x actually looks like. And we're going to investigate it down below a little bit. I want you to remember, though, that whenever you see function of x equals x, you can replace, for all intents and purposes, you can think of that as being a y. So what this is really becoming is an equation where y equals x. And what does that look like? Well, it looks like a straight line with a slope of 1 going through the origin. We go over 1, up 1, over 1, up 2, over 2 up 2, and likewise left 1 down 1, left 1 down 1. Let's investigate the nature of the absolute value of a function by looking at a very simple function, perhaps even the simplest function of all. F of x equals x. F of x equals x right there. All right. So we're going to graph f of x equals x, and then we're going to graph the absolute value of f of x equals x. And the absolute value, we're just going to give it a different name. So this is going to be the first function we draw right there, f of x equals x. And then we're also going to draw g of x. And g of x is going to be the absolute value of f of x. Okay. Now I know it seems a little bit confusing. Let's do it step by step. Let's first graph f of x equals x, because f of x equals x, I hope you recall, is very similar to thinking of it as y equal x. Y equals x. Okay. And that's just a straight line with a positive slope of 1. When x equals 0, y is going to be equal 0. When x equals 1, y is going to be 1, and so on. Okay. And if we were to investigate x in the negative direction, x equals -1, well, y would be equal to -1 as well. And x equals -2, y equals -2, and so on. And what this does is it gives us a fairly nice straight line that goes through the origin with a slope of 1. All right. So this is f of x equals x. So now let's try to figure out what g of x is, where g of x is the absolute value of x. And we're going to use a table of values for that just to show you the conversion. So here is x, and this is g of x equals the absolute value of f of x. And what I mean by that is if x equals -3, well, the absolute value of -3 is, according to the rule of absolute values, stripping away the negative sign, 3. Likewise, the absolute value of -2 is going to be 2. The absolute value of -1 is going to be 1. The absolute value of 0 is interesting. Well, it has no negative sign, so it looks like it's not going to change. The absolute value of 0 is, in fact, and will remain 0. And then we go into the positive numbers. Absolute value of 1 is simply 1. The absolute value of 2 is 2, and so on. So now we just have to graph this thing and see what it looks like. Where do you want to start? Well, let's start at the left side at x equals -3. When x equals -3, that's over here, y is going to be +3 right there. There's x value here, and there's the corresponding y value. When x equals -2, y is going to be +2. And when x equals -1, y is going to be -1. When x equals 0, y is going to be equal to 0 as well. And now you're going to see a little bit more familiarity here. When x equals 1, y is going to be equal to 1. When x equals 2 is 2. When x equals 3, y is 3. And so on, and so on. And even though we don't go that high, you can easily continue the pattern. And even though we don't go below -3, I think you can see very easily that the pattern continues in that direction as well. All right, so what does that leave us with the graph? Well, it leaves us with a graph that sort of looks like the first graph, but with a little bit of a difference. This is going to be g of x right there. So for all of x values that are 0 or greater, it just looks like f of x. But for values that are less than 0, g of x, that is the absolute value of f of x, looks like it's been transformed. It's been mirrored, hasn't it, about the x-axis. What an absolute value does to a function is it breaks it up into two parts. So you'll see that there's a part of the function that is less than 0, where the x values are less than 0. And then there's also a part of the function now that becomes greater than 0. But not just greater than, but greater than or equal to 0, because on the right side of the graph, we're going to include the 0. Because as you see from the piecewise function on this side, if you see this part here, absolute value of 0 is 0. It doesn't change. The absolute value of a function doesn't change for x equals 0. So x is included in all of the part of the graph on the right. So that's why it's x is greater than or equal to 0, and not included for x less than 0. So let's go back up here and look at this definition, see if we can't figure out a little bit about what this definition means. The absolute value of x equals x when the x values are greater than or equal to 0, but it equals to negative x when values of x are less than 0. So let's take a look at values of x that are greater than 0. So let's look at x equals 4, and let's try to take its absolute value. The definition of absolute value says that for x greater than or equal to 0, and we have that, then the absolute value of x is simply x. Now let's choose a number that's less than 0. A number of less than 0 would be, I don't know, -3. How's that work? Okay. And let's take its absolute value. Definition for absolute value says that for the absolute value of x, if x is less than 0, and this -3 is quite clearly less than -0, or less than 0, then the absolute value of x equals negative x. So the absolute value is going to be negative x. And negative times the negative, of course, is 3. So there's your absolute value of -3. All right. And so what we're doing here is, with the absolute values, we're creating a bit of a mirror image on part of the graph, and we're creating two parts of the graph. Notice that these two intervals are not overlapping. The right segment includes 0. The left part of the graph does not include 0. If both of them included 0, if this was both x equals greater than or equal to 0, or less than and equal to 0, you get a situation where you had an overlapping value at x equals 0. And from what you remember of definitions of functions, for any x value, there can be one and only one corresponding y value. So that couldn't be that could never happen to you. So for x equals 0 and greater, you always get one part of the graph. And then for x equals, for x of less than 0, you get a bit of a transformation. You get a reflection about the y-axis. So you get those two parts. So let's take a look at these two parts and try to figure out what we call them. So this is the part here where x is greater than or equal to 0, right? It includes 0, and it's unchanged. The absolute value graph is the same as the graph of the regular function. And because the points don't change, we give them a name. We call these invariant points. Okay? That's an invariant point. This is an invariant point, invariant point, invariant point. And for parts of the graph that are less than 0, what you've got is a reflection about the x-axis of all your y values. Let's take a look at the domain and range of g of x now, of g of x. The domain and range don't seem to have changed at all. They still can go on forever and ever in the left direction of x, so in the negative direction, and in the positive direction. So it doesn't look like at first blush that domain and range, that the domain changes. It still is from negative infinity to positive infinity. The range, however, does look a little bit different. Notice that there are no negative values for y. The range begins at 0 and includes 0, and that's how we write that, but then goes off into the positive y direction, goes up and up and up forever. So there we go. Okay. So the range has changed, but the domain hasn't. So take a look and compare f of x with its absolute value. And it's that feature of the y values changing that is really what's happening when you take the absolute value of a function. Let's take a look now at putting into words what we think we've figured out here. Can we use the graph of f of x to determine what the graph of its absolute value function, g of x, is? Well, I think we can. I think we can. So the first thing we'll say is that when f of x is greater than or equal to 0, g of x, or its absolute value, is the same. All right. What about when f of x is less than 0? F of x is less than 0. Well, when f of x is less than 0, g of x is reflected. About the x-axis. And we call this a vertical reflection. The reflection is up and down. So in the up and down orientation is vertical. And so that kind of summarizes then what all these looks like. It shows us, the important thing to know is that when you take the absolute value of a function, you're going to end up with two parts. You're going to end up with the part that is greater than or equal to 0 and a part that's less than 0. And the definition we use for that, this is another word that you have to become familiar with and learn, is called piecewise. It is a piecewise functions. Piecewise function. And what we mean by that is two parts. What two parts? The part that's greater than or equal to 0 for x values, and the part where the x values are less than 0. So there's always going to be two parts to an absolute value function. We are on page 167, so let's see if we can't do some examples and have this make a little bit of sense. There we go. Given the graphs of f of x and g of x, and just to let you know what we're talking about, there's f of x, there's g of x. We're going to do each one individually. Given f of x and g of x, sketch the graphs of their absolute values and determine the equations of the original line. So it's asking us for the equation of the original line, and it's asking us for the absolute value of that line. So let's do the simple stuff first. What do we know? What do we know? Well, when we have a line, we can figure out the equation of that line by finding a y-intercept, and we do have a y-intercept of at 4. So if x equals 0, y equals 4. That's good. And we can also figure out a little bit, we can easily figure out the slope by choosing a couple of points that the red line crosses. So it crosses at 0, 4, and it also crosses at 6, 0. So if I wanted to figure out, and I'll erase these afterwards, but if I wanted to figure out the slope, I could use those two lattice points as a guide, and slope would then equal, well, it's a slope that's going down. The line is going down, so it's a negative slope. and it's going down 1, 2, 3, 4, 4, and over 1, 2, 3, 4, 5, 6. So it's negative 4 sixths, all right? And that can simplify to negative 2/3. So we have an original line with a slope of negative 2/3, sorry, a y-intercept of positive 4. So we can just rile off an equation. F of x is going to be equal to negative 2/3 x plus 4. Straight slope-intercept form for the equation of a line. Now, it's asking for the, let's just check it out here. It wants us to sketch the graphs of the absolute value of this, okay? It's not asking us for the piecewise function, but we're going to do that anyways. The absolute value graph is going to look very similar to the original graph of the original function, but this point here where it crosses the x-axis is going to be important, because from here on in, moving to the right, wherever the y values are negative, they're going to be reflected about the x-axis. So here's a lattice point that's 1, 2, 3, 4 below. It'll go 1, 2, 3, 4 above. So if I'm just sketching the graph of the absolute value, it's going to look like that. All values for y that are negative after x equals 6 are going to be reflected about the x-axis. And so now what we want to do is probably state the piecewise functions as well, because in the original function, the formula of the line is set. That's the original red. But when we're dealing with piecewise functions now, there's going to be two parts. There's going to be the part of the line where x is less than or equal to 6. And for that part of the graph that is less than or equal to 6, the equation of the line is going to be negative 2/3 x plus 4. But for the part of the absolute function curve that's greater, that has x values greater than 6, so for x greater than 6, the equation of this line, well, you can figure it out. You'll know that the x-intercept will be negative 4, and it'll have the same slope, but negative. So the equation of that line is going to be 2/3 x minus 4. And now you can compare the two equations, and you can see what, well, you're going to learn this word in a little while, the reciprocal is of the line. You can see very clearly that the reciprocal equation of a line, you simply change the signs of all the parts like that. So there's the piecewise function right here. And I think we have adequately answered this question. So you may be wondering when to use x is less than or equal to 6, or whether you should use x is greater than or equal to 6. And the answer to that lies in understanding whether, well, if it's a straight line, whether the slope is positive or negative. Because if the slope is negative, then you're going to be interested in all the values to the left of the x-intercept. And if the slope is positive, all the values to the right. So on the right here, we have an example of a question that has a positive slope. And let's see how the piecewise function changes and which x is greater than or equal to. So first of all, we're going to identify x equals 6 as being an important point. So there's going to be, for the piecewise function, a part of the equation for part of the graph is going to be for x greater than or equal to 6. And then there's going to be another equation for the function that is less than 6. Greater than or equal to 6, because after x equals 6, the line all of the line lies above the x-axis. And it's just the parts of the graph where x is less than 6 that's going to be flipped over. All right. And I'm just going to write this down here instead because I'm going to need the space up there. So x greater than or equal to 6 is going to be one equation. X less than 6 is going to be another equation. All righty. Well, let's try to figure out the equation of the line. We're going to do it straight up by inspection. Let's just look at the red line to begin. It's got a y-intercept of -3, and it's got a slope of 1/2 x minus 3. All right. And so for the piecewise function, that is the equations for the absolute function of this, for that part of the graph that's greater than x equals to 6, it's going to be the same. And for that part of the graph where x is less than 6, we're going to take the negative x coefficient, change the sign on the 3, and that gives us the reciprocal equation of the line. Think of it as being an opposite of sorts. And if you want to double check, you could just work the way, well, we're going to draw the graph backwards anyways. So let's take a look. We know it's going to have a negative slope of 1/2, so that this is going to be a point on the graph, and this is going to be a point on the graph, and this is going to be a point on the graph. So there is the absolute value. And now very clearly you can look at the equation of this part here. X or y-intercept of +3, it's got a -1/2 slope. So the equation of this part is -1/2 x plus 3. The invariant points, that is the points that don't change, on a line with a positive slope will be on the right side. And over here, the invariant points will be on the left side. Cool. Our next example gives us a variation of the question. So there's lots of different ways we can pose a question here. Okay, we can give you a graph and ask you to figure out the original equations and what are the absolute value equations, both of them, because there's two parts. There's a piecewise formulation of an absolute value graph. And that's what's happening here. We're given a function and it's asking us for a whole bunch of stuff. The intercepts, sketch the graph, state the domain and range, and express as a piecewise function. So understand that the absolute value of 3x plus 1 comes from something. Let's look at the original line. Instead of y equals the absolute value of 3x plus 1, let's look at a function called y prime, or a line called y prime. And y prime is simply going to be 3x plus 1. And we're kind of curious to see what that line is going to look like. And I think it's a good place to start. So what does a line of 3x plus 1 look like? Well, it's got a y-intercept of 1 right there. And it's got a slope of 3. So from here, we're going to go over 1 and up 3. So we know that that's going to be a point. Over 1 and up, and 3 would bring it off there, but it'll be around there. Likewise, we can go left, 1 over to the left and down, 1, 2, 3. So -1, -2 is going to be on that line. So here is the line y prime. But we're not interested in y prime. We're interested in the absolute value of y prime. So let's change colors here and let's do green. So y is going to be the absolute value of y prime, and that's expressed there. All right. One of the first things you should probably do is try to figure out the x-intercept. And so to figure out the x-intercept, we're going to have to do a little bit of remembering of how to do that. For an x-intercept, y is equal to 0. So we're going to have the absolute value of 3x plus 1 and make it equal to 0 and see what we get. Now, the absolute value of +3 is just 3, and the absolute value of +1 is just 1. So we can just remove the absolute value signs because they'll have no effect. 3x is going to be equal to -1. X is going to be equal to -1/3. And does that make sense? Does this look like -1/3? I think it does. I think it does. And that x-intercept of negative 1/3 0 is going to be important, because that shows you the point at which you get the two parts of the piecewise function. So for that part of the graph that is greater than negative 1/3, where x is greater than negative 1/3, that's what the graph's going to look like. And if we start checking off what we want to do here, well, it says determine the intercepts. So the x-intercepts are at, or the x-intercept is at negative 1/3 0. And the y-intercept is going to be at 0, 1. So we've done that. Good. Done. Sketch the graph. Well, I think that's probably what we're going to do next. To sketch the graph, you're going to have to figure out where the tipping point is. At what point does the vertex of the V come? And that's why determining the x-intercept was really important. So we know we have the x-intercept here at negative 1/3. Remember how we chose this point here, negative 1, negative 2? Well, because we know that this is a point on the original function, and we know that that point is going to be reflected about the x-axis, we now know that this is going to be a point on one of the piecewise functions. All right. Now, in case you didn't realize or remember where this negative 1, negative 2 came from, let's just plop in an x value of negative 1 into the original equation, which was 3x plus 1 equals y. So y is going to be equal to 3 times negative 1 plus 1. In other words, y is going to be equal to negative 3 plus negative 2. So there's our point. X equals negative 1. Y is going to be negative 2. Okay, so that's how we got this point. Now, likewise, we might be interested and be able to figure out easily what y value we have that corresponds to an x equals negative 2. So we'll do the same thing. We will substitute x equals negative 2 into the equation. We're going to get y equals 3 times negative 2 plus 1. In other words, y is going to be equal to negative 5. So we know that down here somewhere at negative 5, way back down here, that there's a point on the original line. But we're interested in the piecewise function of the line, and so that point, negative 2, negative 5, is going to be reflected about the x-axis, and it's going to turn in here. So we've got 2 points on the left side of the piecewise function. So we can go ahead and draw the line, sketch the line as best we can. And I think then now we've got the sketch taken care of. And the next thing we ought to do then is just figure out what the equations of the piecewise function are. So remember, we started off in blue. This was the original line. And when you took the absolute value of that, we got something a little different. We got a little bit of the same, a little bit. So this part here stayed the same, but this part got reflected from that. All right. So now we have to state the 2 piecewise parts of the absolute value of this curve. And they're going to look like this. There's going to be a part where x is greater than or equal to negative 1/3. And the equation of that line for where x is greater than or equal to negative 1/3 is simply going to be 3x plus 1. And the part of the graph that is less than negative 1/3, the part of the graph for x values that are less than negative 1/3, is going to be just the reciprocal of 3x plus 1, which is going to be negative 3x minus 1, just like that. There's the 2 piecewise functions. So we can knock off question D now, and we are left with the domain and range of the absolute values. Let's change colors again, and let's look at the domain and range of the line in green. The line in blue is easy. there is no restriction on x. X is all real numbers, because x goes forever in the right direction and forever in the left or the negative direction. But when you take the absolute value, some things change and some things don't. So for the green line, the domain is going to be in interval notation unchanged. It's going to be all of the negative values of x and all of the positive. It goes into infinity both left and right, into the negative side and to the positive side. But for the range, notice that there are no values for y that are less than 0. So for the range, it's going to be 0 on the bottom side to infinity on the top half. So greater than or equal to 0. And if we wanted to express this using interval notation, we could do that as well. And let's just change a color here. The domain then would be the set of x values such that x is a member of all the reals. So there's no restriction on x. X can be any value within the real number family. Range will be all of the y values such that y is always greater than or equal to 0, because x or y could be equal to 0. When y equals 0, x equals -1/3. So that's good. And as long as it's 0 or greater and a member of the real numbers, we are happy. So there's your domain and range using both interval notation and set notation. And now we are done this question. Moving right along to page 168. 168. All right, just a couple of really quick questions. And now we get to cut corners, because it's not asking us to sketch it. It's not asking us to figure out what the original equation was. Express the function g of x equals the absolute value of 2x plus 4 as a piecewise function. Piecewise function. All right, so how do you attack a question like this? A good first thing to do is to figure out what your x-intercepts are. Because once you figure out where your x-intercept is, then you know where the vertex of that v, you know that it's going to look like that. Right now, you don't know where the axes are. It could be like that. Who knows, right? But you know, if you know what your x value is, then you know that part of it is going to be that equation, and then part of it is going to be the reciprocal and so on, right? So let's figure out the x-intercept. X-intercept when y equals 0. And y equals 0 when 2x plus 4 equals 0. In other words, when x equals -4. In other words, when x equals -2. There we go. So the x-intercept will be -2, 0. Okay. So your the two parts of your piecewise function are going to be for that part of the line where x is greater than or equal to -2, and then part of the line where x is less than -2. All right. Now, you can tell a lot from this right here. You can tell that the slope is positive to begin with. So the original line is going to look like that. And the absolute value line is going to look like, let's use that color, like that, where this value right here is -2. So the x-axis is there, and this would be the y-axis. So what I drew originally is actually pretty cool. So part of the equation where x is greater than -2, in other words, right here, is just going to be the original function, 2x plus 4. And for that part of the absolute value function that is less than -2, it's simply going to be the reciprocal equation for this line. So if this line is 2x plus 4, this line here is going to be negative 2x, negative 2 because it's negative slope, right? The opposite of positive slope is a negative slope. The slope itself, the magnitude of the slope itself will be unchanged, but the y-intercept is going to go down there and it's going to be flipped over the x-axis as well. So there's your two bits right there, your piecewise function for the absolute value of 2x plus 4. And finally, one last question here. Given the graph below, express the graph as a piecewise function. So the problem we're faced here is similar to the issue we had when we took the square root of a number. Remember that the square root of x squared is plus or minus x, right? Because you don't know whether there was a negative number squared and you lost that information inside the radical sign, right? Well, we got the same issue here. We don't know what the original function, the absolute value of which you're looking at in here. So the original function could have, I think you can see, could have been this, right? And then we simply found the x-intercept, and then you found the part of the piecewise function of that. But similarly, I think you can see pretty clearly that this could also have been the original function, right? So if blue is the original function, then that part of maroon up on the right side is the piecewise, the second part of the piecewise. But if the maroon was the original function, then the left part of the blue would have been the original. So we're going to have, all of this to say is that we're going to have two possible answers for this, all depending on which one was the original. So let's go back here and let's look at blue, and let's change pen sizes. All right, so let's call this h of x 1, okay? That's the first option. And then we'll call the other one h of x 2. There's two different options. If h of x sub 1 was the original, then the absolute value would have been negative 2x plus 4. Now, how did I get that? Well, that's the equation of the line in blue. There's the plus 4, it's the x-intercept, okay? And negative 2 is just the slope, and we can just read that off, right? It's got a run of 2 and a rise of negative 4. So negative 4 rise over run, negative 4 over 2 is negative 2. So negative 2x plus 4 is just the equation of that first line, all right? Well, let's look at the other side here. What would the equation of the other line be? Well, it would just be the reciprocal of negative 2x plus 4. In other words, 2x minus 4. And take a moment and see if that doesn't make sense to you. The magnitude of the slope are the same. It's just the direction are different. So we've flipped the direction from negative 2 to positive 2. And I think if you follow the line down, you'll see very easily that you'll get a y-intercept of negative 4 instead of positive 4. So the two reciprocal equations here are fairly easy to read off. And so now what we want are the piecewise functions for each of those. So let's change colors again. And let's start with h of x sub 1 in blue here. For values of x that are less than or equal to 2, the equation of the piecewise equation of the absolute value will be negative 2x plus 4. And for values of x that are greater than 2, the piecewise, that part of the piecewise function will be positive 2x minus 4. Let's look at h of x sub 2. Remember, this is h of x sub 2, okay? The other possible option. And once again, there's two parts. It all revolves around the x equals 2. So for x greater than or equal to 2, the original function will be the original function of 2x minus 4. But for values of x less than 2, the equation of the line will be the reciprocal of 2x minus 4, which is negative 2x plus 4. And I think we have done our bit here. We figured this out. It all depends on what was the original, and we don't know what the original was because we sort of lost that information by taking the absolute value of something. Just like taking the square root of a number squared, you lose information about what the original number was. So there you go. Go forth and calculate. Page 169, begin your sample questions. As usual, the answer keys are posted, so happy mathing.